Hey everybody, welcome to my talk. I'm Shashank at AWS, and in this talk I'll be talking about how Docker runs machine learning on specialized machine learning hardware. What do I mean by specialized machine learning hardware? These are sometimes known as AI accelerators. These are additional processors that sit next to your CPU or central processing unit in order to accelerate machine learning workloads. You may be familiar with NVIDIA GPUs or custom silicon accelerators such as AWS Inferentia, Intel's Habana Gaudi, and there are many others. So these are all processors that sit next to a CPU that are very good at doing parallel processing or parallel tasks, which are very common in machine learning applications. Together, they're often called heterogeneous systems. So we'll take a look at how Docker handles these extra hardware devices. Now, as I was preparing for this talk, I wanted to jump right in and talk about the internals of Docker and how it manages different runtimes and pre-start hooks and all that. We'll get into that. But I realized that the machine learning community and the Docker community are often very different in the sense of their day-to-day work and where they spend their energy and effort in. So the machine learning community, which I consider myself to fall under, often find technologies like Docker and Kubernetes and orchestration systems to be a sort of alien. They're not easy to grasp by a machine learning practitioner, a data scientist, and the same is true the other way around. Someone in the Docker community may not be fully aware of the needs and requirements of the machine learning community, and oftentimes there's a jargon or phrases and technology that you use mismatch in the sense when you talk about certain technologies and phrases in the ops and the container community, it kind of falls flat when machine learning practitioners thinking about it. So I wanted to start this talk off by talking about some of the challenges in the machine learning community and how Docker addresses it and how machine learning accelerators, AI accelerators, are a big part of that and how Docker addresses that. Okay, so let's jump right in. So how is machine learning development to deployment different from a traditional software development to deployment? So as you, at a very high level, broad sort of a simplistic classification, right? There's a development phase, there's a deployment phase. Of course, this is oversimplification, and the coder or the software developer is mostly concerned with code, writing code, and then deploying this as maybe microservices in the cloud using containers. And of course, there's CI/CD and all the ops stuff that fall in between. But broadly, these are the two steps. Now, machine learning also has these two steps. Only difference is that the initial development phase also includes machine learning model development, which includes training. And there are two other components in addition to code, which is data sets. So it's important to have access to large data sets and specialized hardware like GPUs and other training processors like Intel Habana Gaudi. So these specialized processors work with your CPU in order to accelerate training. So these two are different and unique to machine learning compared to traditional software development. And similarly, on the deployment side of things, you again need access to hardware. If you really want to keep your latency down, if you want fast results, high throughput, be able to cater to hundreds and thousands of or millions of requests coming in, you want access to a specialized hardware that can process this very, very quickly. Okay. Now, let's take a look at the anatomy of a typical machine learning stack. Now, we know software stacks are complex, frameworks are complex, and that's the whole point of frameworks, right? They abstract away all the underlying nitty-gritties. So this may look familiar to you, right? Pretty complex stack. Now, the top part of it, what I highlight here is your typical libraries and frameworks and your code. So this is something you're familiar with as a software engineer, and you can containerize these and deploy them, and you get all the benefits of packaging and isolation and all that, right? But machine learning stacks also has these other components that make them unique. So there are hardware specific libraries in a typical machine learning stack. These include accelerated libraries that target the processor that's not the CPU. So your GPUs or your other accelerators like AWS Inferentia, and these libraries or primitives as we call them, accelerate some of the mathematical operations such as matrix mathematics, matrix multiplication on the accelerator device, not on the CPU. Okay, so these now start to get hardware specific. So you're getting a little more locked into a platform, which is counterintuitive because Docker is supposed to be platform and hardware agnostic, right? And then of course there is the processor and the CPU, so it's sort of a heterogeneous system where you have a CPU and your accelerator. I'm using the phrase AI accelerator interchangeably with machine learning specialized hardware, right? These are basically your extra processor. Now, this is counterintuitive to sort of the benefits of Docker, in the sense containers are supposed to be hardware agnostic and platform agnostic, but now you have hardware specific libraries and platform specific libraries. So how does Docker handle this in a typical machine learning stack, whether it's for training, model development, or deployment, as in hosting AI machine learning powered microservices in the cloud, right? So some of you who are Docker experts may say, wait, but Docker already supports hardware devices, right? You can do Docker run -- devices, map your devices to the container, and the container has access to your hardware, and you're all set, right? It's partially true. The solution here is that you can actually encapsulate not just the CPU portion of it, but also the hardware accelerator libraries, such as the AI accelerators and the machine learning AI accelerator libraries, and also the drivers into the container image. Okay, but you also need to have the host. The host OS must also have the driver installed, because the host, that's how the host recognizes the hardware, and then you want to map the hardware into the container, and you also need the driver in the container, so that the stack above it has access to the hardware. Okay, it starts to get a little more complicated, and the challenges here is that you're duplicating driver installations, where you're installing it in the host, but also installing it in the container image, which bloats the container image and size, which, as you can imagine, be challenging when you deploy this in the cloud. But also, if there's any slight mismatch in the driver versions, the whole thing is brittle. It just breaks down, and this is a huge challenge. It sort of undoes all the benefits of Docker, because you're getting in this sort of lock into a specific hardware and versions and drivers and all that. Makes it not portable. Again, makes it difficult to scale. If it's not portable, it's difficult to scale. So previously what people did is just not use Docker. They just use VMs with the whole stack and the drivers installed, and the only portability was the user code. But then the disadvantages of doing that, right? Because you don't have portability anymore. If there's slight variation in the library version, everything breaks down. So basically there was no solution. There was no good solution, right? Docker supported hardware, but it was sort of a brittle sort of a solution. Okay, so before I jump into how we address it and how Docker addresses it, I want to give a quick crash course on why we actually have hardware accelerators. So typically in your machine learning, in your traditional software stack, most of the code is executed sort of in a serial manner, sequentially. Whatever parallelization is handled by the CPU cores, and that is sufficient. But in machine learning, most of the operations happen to be matrix multiplication. Yes, machine learning sounds complicated to some people, but the fundamental operations are just matrix multiplication. And turns out this is highly parallelizable, and you can offload it to an extra processor, which is why we have so many additional processors, and arguably the most popular one are NVIDIA GPUs, right? So that's where all of this gets offloaded to. And I have a blog post that I linked here where I talk about the motivation of processors, why they exist, what benefit do they offer on top of CPUs and all that. It's introductory read, which goes into sort of the motivations. If you're interested in this topic, feel free to check it out. It's linked on the slide. So now we'll get to the meat of the presentation, which is how do we make sure that Docker is able to take advantage of specialized hardware like GPUs and AWS Inferentia, which are the two examples I will use. But it extends, similar pattern extends to all sorts of other hardware. Okay. Before that, let's do a quick refresher recap on how Docker actually creates a container process. Now, again, you're part of the Docker community, I presume, so this might be super familiar to you. So let's start here as a recap. So what happens when you do Docker run, right? Docker, the whole toolchain, is responsible for guiding you through the process of creating this container process. And underneath there are different layers. This is quite a oversimplification of all the different processes that happen. But broadly, your specification adheres to an OCI Open Container Initiative specification that runs the library that manages creating these container processes expects. Okay, so whatever you use using the Docker command line tool is translated into or formatted into the spec and is given to runc, the library which is then responsible for creating your container process. And this is what happens when you say Docker run your interactive or whatever it is. Okay, good, all good. Now let's see how hardware can feature into this sort of a workflow. Okay, first, this looks complicated, but I'll walk through it step by step. I promise it's not that complicated. Okay, so first, when you look at Docker run, we'll add an extra command line option here. It should be -- runtime is, let's call it a custom runtime. Now whatever I'm showing you here is sort of a standard template for adding hardware support. Okay, I'm not talking about GPUs or AWS Inferentia or anything specifically. I will come to that, but what I'm showing you here is sort of a standard template. Okay, first you need to define this custom runtime. Okay, why do we need to have this custom runtime? So Docker lets you, of course, specify custom runtimes, and this custom runtime in this case is sort of a shim. It takes in this request in the OCI specification, intercepts the specification between runc, and then adds something called the pre-start hook. Okay, so it takes in to recap, it takes in the specification, keeps it as it is, add a pre-start hook, I'll talk about what it is, and gives it off to runc. Okay, that's the only change it does. Now the pre-start hook is responsible for adding hardware support. Okay, how does it do that? Now runc, as I mentioned, is responsible for creating your container process. Now because as a pre-start hook, you're instructing runc to perform a series of steps before the container process is created. Okay, what are these series of steps? In our case, the series of steps is you define a hook configuration. Now this hook is responsible for injecting or exposing the hardware into your containerized environment. Okay, now the benefit of doing this versus what we showed before, where we had to install the driver into the container environment, you don't have to do any of that now. The driver remains in the host system. So here's what happens: the custom hook then talks to a library, and this library is specific to the hardware vendor. If it's a GPU, it's an NVIDIA library. If it's AWS Inferentia, it's a AWS Neuron library. So this library is responsible for communicating with the driver, which is in the host OS, and the driver in turn, of course, talks to the actual device, the hardware device. And once it talks to the driver, figures out how many devices on the system and how many cores and other information, runc then creates the container process, and the library then exposes. It does all the things that you would have done manually, like mapping the device. So /dev/NVIDIA or whatever the hardware option is, it maps it onto the container environment and then exposes the hardware into the container environment. Okay, so the sequence of steps here and custom libraries are responsible for giving you this sort of a seamless experience. So from a user experience point of view, the only change you're going to do is Docker run, specify a runtime. The runtime will add all these other features because the runtime will add the hook, pre-start hook. The pre-start hook will call a custom library. The library will talk to the driver and then expose the driver into the container process. Okay, so these are all the steps. From a user point of view, as I said, no changes. There are a few other environment variables that you can specify to say if you had multiple hardware options on the same system, then you only want to make the first and second available in the container, and in yet another container process you want to make the third and fourth available if you have 4 accelerators, for example. Okay, those are things that that you can specify. Now let's take a look at a specific example, the same template pattern I discussed, but for NVIDIA GPUs. Okay, arguably the most popular accelerator for machine learning are NVIDIA GPUs. It's available pretty much everywhere. You can go buy a gaming GPU and run Docker on it, right? So what's happening behind the hood? So NVIDIA has NVIDIA Container Toolkit. It's a bunch of libraries that aid you to enable GPU support in Docker containers. So when you do Docker run with runtime NVIDIA, and in fact the latest version of Docker, you don't even need to specify that the support is enabled by default. So what happens is, again, we use Docker run, the OCI specification, again, Open Container Initiative. The benefit of it is it sort of works with multiple container runtimes. In this case, we're talking about Docker. So NVIDIA Container Runtime, it's a shim, as I mentioned. It just takes the specification, injects the pre-start hook, and hands it off to runC. And runC, who is responsible for running the container process, calls NVIDIA Container Toolkit, and which is responsible for calling a library called libNVIDIA Container, and that in turn talks to the NVIDIA driver on the host, which talks to the GPU and figures out how many GPUs are there in the host. And then after the container process is created, the library is responsible for exposing. It maps the devices into the container process and gives you access to the GPU process inside the container process. Okay. Now, let's actually take a quick look at a demo of what this looks like before I jump into the other hardware which I'll discuss, which is AWS Inferentia, just to show you that they're not really that different. Once you support one hardware, supporting other hardwares is pretty straightforward. Okay, I'm here on the AWS console where I have 2 instances running. One is the GPU instance, which is says P3 Ubuntu. It's a type of GPU instance on AWS, and Inf1, which is the Inferentia accelerator. So I'm going to start with the GPU instance. And one of my favorite new feature in the AWS console is I can connect an SSH to the instance right in the browser. I don't have to pull up a terminal. So I love this feature. So you just click on it and you have access to the terminal, and I pull up my tmux session and I'm good to go. Okay, so let's see where the runtime is. Okay, so if you go take a look at this etc docker daemon.json, you'll see that you can specify runtimes for Docker, and the runtime here is NVIDIA, and the path is NVIDIA Container Runtime. It's already on the path, so that's what it invokes. And this is, if you go back to the slides, is this, exactly this. Okay, now you can also add an additional specification here that says default runtime. So you can specify default runtime is NVIDIA. If you have multiple runtimes, runC is obviously the other runtime where the specification directly passed to runC. You can have additional runtimes here, and actually that becomes very important when you actually use Docker support on Kubernetes, where it expects the default runtime to be enabled, but it's not enabled here. But that's another thing you can specify. Now NVIDIA, the way you can specify configuration for the runtime is through sort of a file-based config. Different libraries implemented differently. NVIDIA chose to do a file-based config, and here there are a bunch of things that you can specify. You see there are other runtimes that are specified here, and if you want to keep other paths for certain variables, you can do that. If you want to change the path to libraries and all that, so you can do that in this specification file. Okay, so let's take a look at I have one Docker image here, and this Docker image is a TensorFlow container. Now let's go run this. So Docker run interactive remove container. Let's start over again. Docker images, Docker run interactive rm. Let me copy this container image ID, and yeah, let's go see what happens. So I'm within the container process environment. Now the way to check if you have access to GPUs is to run this nvidia.smi. Okay, so I ran nvidia smi and it says command not found. Okay, so right now my container environment doesn't have access to NVIDIA GPUs, but why so? Let's exit and see why this is the case. So let's see if we can access GPUs in the host OS. Okay, it seems that I can access the GPUs. You'll see here that it says Tesla V100. It's a type of NVIDIA GPU. So I didn't specify the runtime, and I didn't specify the number of GPUs I wanted to access when I started my Docker process. So let's go back to the command I ran. So here I can say runtime equals to NVIDIA, and I can say GPUs equal to all. Okay, so I added two new specification. Now again, I want to highlight that the latest version of Docker, you don't actually need to specify runtime NVIDIA, it'll just work. So now I'm in my container environment, and now if I say NVIDIA SMI, I have access to my GPU within the container. So that is awesome. So basically all the magic that we discussed here happened, and as long as I specified the runtime and the GPUs to give access. So I said GPUs all. I only have one GPU on this instance, so I got access to it, but you can specify I want to give access only to GPU 0, and you can run another container process which gets access to a different GPU. Okay, so that's how NVIDIA works. Now let's take a look at the second example, and there's a reason I'm sharing a second hardware accelerator example, because just to show you how different hardware vendors implement this differently. Now the way AWS Inferentia supports this is a little more transparent, and I'll show you. You can actually see what's going on at the shim level, you can see what's going on at the hook level, and you will get a little more of appreciation. NVIDIA was a little more of a seamless experience, but you didn't have an understanding of what happened behind the scenes. So again, the same steps. The OCI specification goes into the OCI neuron, the shim, which takes it, adds a pre-start hook, calls runC, and the pre-start hook gets enabled, talks to the neuron driver, talks to the Inferentia hardware, and the container process is initiated, and the devices are mapped, mounted onto the process, and then you get access to the library. Okay, so let's go take a look at what this looks like. Okay, so I'll go back to my EC2 instance that's running. This time I'll connect to the Inf1 instance that we just spoke about. Connect through my browser. Love this feature. So I will start off my tmux session. Okay, so where are we? So we'll go to neuron examples, cat examples. Okay, so just like before, we'll take a look at the runtime with the Docker daemon specification, where you can see the runtime, which is OCI default run. So here we actually specify the default runtime as OCI neuron, and we specify the path, explicit path to where the runtime is, and in this case it's just a shell script. With NVIDIA there was a custom library, with Neuron there's a shell script here. We can actually go take a look at what's in the shell script. So remember I said this is a shim. It intercepts the specification from Docker, adds the pre-start hook, and then invokes runC, right? You remember what I said? So let's go take a look at what's inside this wrapper. See, now it's more transparent what's happening behind the hood. First, it's getting the path to runC here, if you see. So here, it's getting the path to runC. And in the next line, it's intercepting it. So it uses a library called OCI add hooks, and uses that library to specify the hook configuration. In this case, The hook is specified in this specific JSON file, okay, OCI neuron hook config.json file, and then it specifies the runc path and passes all the command line arguments that this script gets back into runc. So it's transparent now, so you can see how the shim works. So it's taking the specification, adds the hooks using this library called OCI add hooks, which by the way is an open source library that AWS open source. It's on GitHub. And then it calls the runc by passing all the same command line arguments with the hook onto runc. So it's so much more transparent here. Now let's take a look at what the hook config looks like. Okay, so this specific hook config, right? Let's take a look at what that looks like. So inside that you'll see what the pre-start hooks looks like. So pre-start, you do pre-start because you want to be able to communicate with the hardware before you start the container process. If you go back to our slide, so this is a pre-start hook, right? You want to be able to talk to the hardware, figure out how many cores are there, how many devices are there, right? So this pre-start hook, again, you specify the path and the arguments, and turns out it's calling a library called OCI neuron hook. Okay, this hook is responsible for this specific hook here is responsible for communicating with the driver and the hardware. So this is what happens behind the scenes when you use AWS Inferentia. Okay, hope that's interesting. It's seamless to you as an end user. You just run it and it just works, right? So hopefully that's seamless to you. Okay, so let's take a look at an example. So you can run a Docker container that is called neuron test. It's one of the Docker images I have. Let me show you Docker images. So Docker images, so I have this neuron test Docker image here. That is what I'm going to run, and I pass an environment variable. Notice I specified the runtime as default. We specified that the default runtime is the neuron runtime, so I don't need to specify runtime. And I just pass an environment variable which specifies which device to expose inside the container process. So if you have multiple devices, you can expose 1, 2, all, right? You specify, and then you run the neuron ls command, which queries the device and shows you that there is one neuron device with 4 cores and all that. So this is the hardware that's on this instance. Okay, awesome. Okay, hopefully that was all clear. Now so yeah, I showed you GPU support, I showed you Inferentia support. Let's take a look at an example of how you might use this, right? As a practitioner, or even as someone who just wants to explore and play with machine learning. So I'm a huge proponent of Docker for reproducibility, specifically in machine learning. Reproducibility is so hard. So I wrote this blog post long ago. Feel free to check it out on why use Docker for machine learning development. It's a few years old, but I think the concepts are still relevant. But I'll give you an example of what I'm talking about here. So let's go back to the GPU instance that we have. Our GPU instance is here. This is a P3 instance. I'm going to connect to it again directly here from the console. And once it connects, I'm going to attach to my existing tmux session, tmux A. Okay. So yeah, turns out I'm still in the Docker container process. Exit. Okay. So Docker images. So I have my TensorFlow container image. So what I'm going to do now is I'm going to run this container image with access to GPUs, and I'm going to also add another argument here that says network equal to host, and this will become clear why. Okay, and then I'm going to run this. I'm in the container environment, and I'm going to install a library, pip install JupyterLab. This will take a few seconds. So essentially what I'm going to do now is I instantiated this container environment which has access to the GPUs in the system, and I'm installing a server which is called a Jupyter server, which gives me access to an IDE. Now this server is running inside the container environment, or it will now when I run Jupyter Lab. Allow root, because we are in root, I say allow root. So now it's running a server, and what I'm going to do now is I can copy this URL here, open up a new tab and paste it here. So what it's going to do is, oh, I need to set up a tunnel. How did I forget? Okay, let's go set up a tunnel. So now the server is running in EC2. I want to set up a tunnel to forward those requests to my desktop right here. So to do that, I'll set up this tunnel. Hopefully this is readable. So I do SSH -L, specify the IP address and the port to map to, and my SSH key and the URL. Okay, so I did that. I set up the tunnel. I go back and run that again, and voila, I have my machine learning IDE all set up. And this IDE is not just running on my host, it's running inside the containerized environment. So what I can do here is just confirm that I have access to the GPUs. Yes, I have access to the GPUs, and you can see this is the container environment. It's not the host, it's a container environment. Now why do I want to do this? Now if I start testing my code and developing here, I know exactly what container this is, what container environment this is, where I got the image. If I'm able to reproduce my code here, I can guarantee that someone else will be able to reproduce my code in a similar container environment, which is why I loved writing code and testing inside a container environment, which is arguably not the main reason why people use Docker containers, which is primarily focused on deployment. But in machine learning, at least, I love using this as a development environment. Of course, there are benefits to doing this with deployment, of course, right? You can ensure that you can scale processes using an orchestration like Kubernetes. Speaking of which, the last topic I want to talk about is GPU support on Kubernetes. I say GPU support, but same applies for AWS Inferentia and other hardware. The key difference is that once you set up a cluster, AWS offers a command line tool to do this. You set up a cluster. NVIDIA offers this device plugin that you can apply. So you do kubectl apply this device plugin. There are prerequisites that each node on your cluster should already have access to the driver and should have the container runtime, container toolkit installed. So the container doesn't need to have the driver, just the host. And then you deploy this daemon set, this device plugin, and this is responsible for advertising GPUs into the containers inside each pod that you provision for, deployments or training or whatever it is, the job or deployment that you submit. Okay, that's the benefit of doing this. I won't get into details of this. This is a whole another topic and whole another talk. But this is very interesting on how to expose GPUs into your cluster so that you can have dedicated node groups that are accelerated devices and dedicated node groups for non-accelerated devices. Then some data scientists who want to train can access those for a training cluster, or you can have another one for model hosting where you deploy a model serving container that has access to the GPUs and can serve low latency, high throughput sort of requests. Yeah, so that's about how Docker supports hardware, and I spoke about a lot of resources. I'll touch upon a few ones here. Let me go back to my browser and I'll mention a few things. So if you're interested in why hardware, I have a blog post called AI accelerators and machine learning algorithms, how they're evolving together, why are there different types of hardware and what are the different types of hardware. If you're interested in it, it's fairly introductory but also goes into some of the specifics. I have other blog posts that talk about different types of hardware and also how to choose the right GPU for your deep learning. So feel free to check those out. And the other resources I'll mention is, of course, the documentation page for AWS Inferentia, which is the Neuron SDK, and also the documentation page for NVIDIA GPUs, which is called the cloud native libraries by NVIDIA. So feel free to check out those documentation pages. which again goes through some of these concepts. And with that, I come to the end of my presentation. I hope you found that interesting. I know it's a little different than what you would have likely heard in a typical Docker sort of meetup, but Docker's big in machine learning. A lot of people use it. On AWS SageMaker, which is a primary managed solution for machine learning, is completely runs on Docker. It's the easiest way to scale for training, for experimentation, for deployment. So it's pretty huge in the community. So thank you for listening, and I hope you enjoyed it. And if you have questions, feel free to reach out to me on any of these links. And I'll see you hopefully in the next community meeting. Bye.